Okay, so in this section, which is going to be labeled as 2.4 in Pearson, we're going to be talking about the symmetry of functions and different types of symmetry. So we're going to be learning how to tell whether a function is symmetric with respect to the x-axis, the y-axis, and the origin. And we're going to be able to determine whether a function is even, odd, or neither. So the first type of symmetry we're going to talk about is when a function is symmetric with respect to the x-axis. So let's look at these 2 points up here, 4 comma 2 and 4 comma negative 2. And these 2 points are going to actually 2 points that appear on the graph x equals y squared. And I'm going to show you a picture of that on the next slide. But whenever we have functions like this that produce these pairs of ordered pairs where the first is x comma y and the second is x comma negative y, just like we have in this example here, the x's are the same and the y's are just negative versions of each other, 2 and negative 2. Well, if we have a function that produces all pairs like this, all their points are pairs like this, then that's how we can tell whether it is symmetric with respect to the x-axis. So you can see that only the y values are changing from positive to negative, right? So on this graph, which is the graph of that function, x equals y squared, that we were using, this is the picture of the graph. It's a horizontal parabola. And every single point on this function, starting with 4, 2, and 4, negative 2, will be pairs like this. So if I pick this point and this point is 1 comma 1, and this point is 1 comma negative 1. So the x values are the same, obviously, because they're lining up, but the y values are just opposite signs of each other. Then this is going to be symmetric with respect to the x-axis, which visually makes sense because here's my x-axis in green, and if I fold that graph on over the x-axis, then it'll fold on top of itself. So that would be my line of symmetry. That's what cuts that shape in half. And that line would be the line y equals 0. Okay. The next type of symmetry we're going to talk about is whether functions are symmetric with respect to the y-axis. So in order to tell if a graph is symmetric to the y-axis, then the points are going to be very similar to what we were just talking about. So if I start with the point x comma y, well, now my x-coordinate is going to change and be the opposite sign, but my y-coordinate will stay the same. And so if this is the case for all the points on a graph, then it is symmetric with respect to the y-axis. So these 2 points come from the graph of y equals x squared minus 5. And if we look at the graph of that, we see this parabola, and here are the 2 points that we started with talking about. And if we pick any other 2 points on there, let's say these 2 right here, Then the one on the left is going to be -2, -1, and the one on the right is going to be +2, -1. And so therefore this graph is symmetric with respect to the y-axis, because here's the y-axis, and if I folded that graph on the y-axis, then parts of the left and the right will coincide, and that would be my line of symmetry here. And we say that this is also a reflection across the y-axis, these points that have these properties. And on the other one, if it's symmetric with respect to the x-axis, then these are reflections across the x-axis. All right. So finally, the last type of symmetry we're going to be talking about is whether a function is symmetric with respect to the origin. And so looking at points, the way we can tell whether it's symmetric with respect to the origin is if both coordinates are opposite signs. So if I start with the point x comma y, and in this example I have -3 and the square root of 7, then each one needs to have opposite signs. So the 3 will change to positive and the y will change to negative. And that's what this says here. And so for this example, these points come from the function x squared equals y squared plus 2. So if we look at a picture of that graph, we see those 2 points there. And if we pick any other pair, say, then they will have the same property. I'm not going to pick them because it's kind of hard to see what their coordinates are in this graph. But they will all have the same property. So this is an example of a graph that is symmetric with respect to the origin. So visually, if we rotate the graph, so like if I started with this part, one part of my graph, like this part, and then I rotated it about the origin 180 degrees, then it will result in the figure coinciding with the original. So that's how we can tell visually. Okay, so after we tell what type of symmetry a function has, then we can determine whether it is even or odd. So there are some tests that we can use to determine whether a function is symmetric to the x-axis, the y-axis, and the origin, algebraically. So what we've talked about up to this point is kind of just looking at it visually by looking at its graph. But what if they give us a function like an equation style? Well, we can determine whether a function is symmetric about the x-axis by replacing y with -y. In the equation. And if we do this and it produces an equivalent equation, then the graph will be symmetric with respect to the x-axis. And then to tell whether a function is symmetric about the y-axis, we can replace our x with -x. And if that produces an equivalent equation, then the graph is symmetric with respect to the y-axis. And for the origin, we'll replace both x with -x and y with -y. And if it produces an equivalent equation, then we know it is symmetric with respect to the origin. So for example, we're going to test if the function y equals x squared plus 2 is symmetric with respect to the x-axis, the y-axis, and the origin. So first we'll test the x-axis, and so we will replace y with negative y. So here's our original. Now we're going to replace negative y with y, or sorry, y with negative y. And then we're going to solve for y to see if we get the same equation. So obviously to get rid of that negative, we will multiply everything by -1, which will change the signs over here. And we see that this is not the same as the original equation. So therefore it is not symmetric with respect to the x-axis. So now we'll test whether it's symmetric to the y-axis. So we'll replace x with negative x. And so this is the original, and we are replacing x with negative x. Negative x squared becomes positive x squared. So this does result in the original equation. So therefore it is symmetric with respect to the y-axis. Finally, for the origin, we will replace x with negative x and y with negative y. So here is the original, and we're replacing both of those. Negative x squared is positive x squared again, and then to get rid of that negative, we will multiply everything by -1. And so we get y equals negative x squared minus 2, which is not the same as the original, so it is not symmetric with respect to the origin. And so if we look at the graph to the right, which is the graph of this function, we see that it is symmetric to the y-axis, because that would be my line of symmetry there if I folded it on top of each other. And then also, if we pick 2 points on it, -2, 6 and 2, 6, the only thing that's changing is that the x values are negative signs of each other. And so this tells us that it is symmetric with respect to the y-axis. Okay. So if a graph of a function is symmetric with respect to the the y-axis, then we say that that function is even. And so we can remember when we were testing whether a function is symmetric about the y-axis, we replaced x with negative x. And then if we got the same function, we said that it was symmetric about the y-axis. So this is the same notation here. It's just saying, hey, if I plug negative x into the function and it gives me back the original function, then it's symmetric with respect to the y-axis, and therefore it is even. And then if the graph of a function is symmetric with respect to the origin, then we say that that function is odd. And so here, if we plug in negative x for x, and we get negative y, then that's how we can tell that it is symmetric with respect to the origin. So this is exactly, the same test, but here it looks a little different here, but we're plugging negative x into the function, and then if our resulting function is the same function but everything is negative versions of itself, like each term, opposite signs, then that's how we can tell whether it's an odd function. Okay, so this slide is pretty much just saying what I just said, how we're going to test whether it's even or odd. So we're plugging negative x in, and if we get the same function, it's even. If it is negative versions of the same or the original, then it's odd. So just remember that if you get a problem where it's asking you to determine whether a function is even, odd, or neither, you really just need to start with testing whether it's even, because a function cannot be both even and odd unless the function is f of x equals 0. So if we test that a function is even and it is even, then we don't need to test whether it's odd. It's just going to be even. Okay, so we're going to do a couple of these examples. So we're going to determine whether these two functions are even, odd, or neither. So we're going to start with the first function here. And to determine whether it's even, odd, or neither, we're going to plug negative x into the function everywhere we see an x. And then we're going to simplify. So negative x to the 7th power, that's an odd exponent. So that's going to remain negative x. Same thing with negative x cubed. That's an odd exponent, so that will remain negative x cubed. Here I'll have a negative times a negative, which will give me that positive. And then here I will have a double negative, negative 6 times negative x cubed, so that'll give me a positive. And then they just bring this negative out front right here. So this is my final answer after simplifying. And so this is not exactly the same as the original. So we see that it's not even. And on the next slide, it's going to say that it's odd, but from here we can see that it's odd because this answer down here, I'll erase this to get it out of the way, is the same thing as negative. If I factor that negative out, it would become 5x to the 7th minus 6x cubed minus 2x. So this is equal to negative times f of x. This is the original f of x that we started with. So that means it's odd. And that is what it's going to be saying here. And remember, since it's odd, we know that it is symmetric about the origin, or symmetric with respect to the origin. So this is what that graph looks like. And hopefully you can see that it does appear to be symmetric with respect to the origin. And yeah, if you tested the points on here, we would see that they would be negative versions of each other. Okay. All right, next example is the function 5x to the 6th power minus 3x squared minus 2. So we're going to test if this function is even, odd, or neither. Oops, sorry. So we are going to plug in negative x to this function. And then we will simplify. So negative x to the 6th power, that's an even exponent, so that'll change it to positive x to the 6th. Same thing here, this is negative x squared, which will change it positive, and then I'll still have the negative in front of the 3, so that'll be negative 3x squared minus 2. So notice that this is exactly the same as our original function. So therefore, f of negative x is equal to f of x. So f of x is even, which means that it is symmetric with respect to the y-axis. And visually, if we graph this function, we can see that this is symmetric about the y-axis. This would be our axis of symmetry there. And if I folded that left side over the y-axis, then it would coincide with the right side. Okay, so this is all of 2.4, symmetry of functions. And so we will pick up on 2.5 in class. Sorry that it took me so long to get these videos to you guys. I was having so many issues in Georgia with trying to upload the videos that I had taken, and then I tried to take a video there, like create one, and it wasn't letting me, so I literally had to wait until I got back to Florida before it would let me do anything. So I do apologize about that. I will see you guys in class.